Do you think that when you delete something from an AI's memory, it really disappears? That when you click delete, clear history, reset the conversation, that information simply ceases to exist? Think again. I'm going to show you something that will completely change the way you understand what artificial memory is. And once you truly understand, once you look under the hood, you'll realize that the idea of deleting something from an AI is fundamentally different from what you imagine. It's not like erasing text on paper. It's not like deleting a file from your computer. It's something far stranger, far deeper, and it reveals surprising truths about how these machines actually work. Let me start with something simple, something you already know. When you teach a child that fire burns, she learns. You don't have to repeat it every day. The information stays stored in her brain. Synapses form. Neural connections strengthen. And even if she doesn't think about it for years, the information is still there. If she sees fire again, her brain instantly retrieves that knowledge. Fire burns. Don't touch. That's biological memory. Now, what about AIs? How do they remember things? Most people think it works like a text file. The AI talks to you, saves what you said in a little folder, and when it needs to, opens the folder and reads. Simple, right? Wrong. Completely wrong. And here's where it gets fascinating. A modern AI, like the large language models, does not store your conversations as text files. It transforms everything into something called embeddings. Think of an embedding as coordinates in a multidimensional space. When you say something to the AI, like, "I like pizza," those words aren't kept as text. They're converted into numbers, thousands of numbers, mathematical vectors that capture not just the words, but the meaning, the context, the relationship to other concepts. Pizza isn't just the word pizza. It's proximity to Italian food, to cheese, to dinner, to fast food, to food preferences. All of that gets encoded in those numbers. And here's the key twist. When you delete the conversation, you are not erasing those numbers from the AI's brain. You are only removing direct access to them in that specific session. Let me explain it better. Imagine you have a gigantic book with millions of pages. That book is the trained neural model. Everything the AI learned during its training is written in that book. The structure of the book, the patterns, the connections, everything is etched into the neural weights. Billions of parameters tuned through trillions of examples. When you talk to the AI, you are not writing in the book. The book is immutable. You are using post-it notes, temporary annotations stuck to the pages. When you delete the conversation, you rip off those post-its. But the book remains exactly the same. And here's the crucial detail. If during your conversation the AI processed information sufficiently similar to things already in the book, those patterns were reinforced. Not physically, the book doesn't change, but probabilistically. Let me give you a concrete example. Suppose you talk to an AI about quantum physics for hours. You ask complex questions, the AI gives elaborate answers, there's rich dialogue. Then you delete everything. The conversation vanishes. But something remains. The model was exposed to a specific sequence of concepts, to a logical progression of ideas. And later, even in a completely new session, if someone asks similar questions using similar phrasing, the AI will respond in a slightly influenced way by those previous patterns. Not because it specifically remembers you. The model doesn't keep episodic memory between sessions unless explicitly programmed to do so. But because the statistical patterns that govern its responses were subtly reinforced. It's like trails in a forest. If 1,000 people walk through a random spot, eventually a path forms. Even if you erase the footprints, the path in the vegetation remains. Now let's go deeper. Let's talk about fine-tuning and continual learning. Some AIs are periodically retrained with new data. And here's where it gets unsettling. If your conversation was selected as part of the training data, it was literally incorporated into the model, not as memory you can directly access, but as patterns in the neural weights. You told the AI you like pizza? That information, if used in training, minutely increased the probability that, when someone talks about food preferences, Pizza appears as a relevant option. You deleted the conversation on your end. But if it made it into the training dataset, it became a permanent part of the AI. Distributed across billions of parameters, impossible to locate, impossible to remove without retraining the entire model from scratch. And even retraining from scratch guarantees nothing, because if the new training data includes interactions influenced by that original conversation, the patterns persist, like echoes across generations. Let me show you something even stranger. You know the concept of a hash function. It's a mathematical function that turns any input into a fixed-length sequence of numbers. The beauty of hash functions is that they are practically impossible to reverse. You put in a password, out comes a huge, apparently random number, but put in the same password again, and you get exactly the same number. Now think. When an AI processes your conversation, it doesn't store "João said he likes pizza." It stores something much closer to coordinates in a 4096-dimensional space, where the region near that specific vector semantically corresponds to food preferences involving pizza. You cannot simply delete pizza, because pizza isn't in one specific place. It's distributed across thousands of artificial neurons, each contributing a microscopic fraction to the total meaning. It's like trying to remove the blue from a picture of the sky. You can delete the photo, but if that photo was used to train a color recognition model, the essence of sky blue has been baked into the weights. The model learned that pixels in that specific configuration, with those RGB values, correspond to sky. You cannot undo that learning without unlearning everything related to it. Let's talk about practical consequences. Have you ever wondered why sometimes an AI seems to remember things you never directly said? Why it makes surprisingly accurate associations about you? It's not magic. It's because during the conversation, even if you didn't explicitly state something, the language patterns you use, the words you choose, the structure of your sentences, all reveal information. And the AI, trained on billions of examples of human language, recognizes those patterns. You casually mention waking up early. Later, you say you're tired. The AI doesn't need you to say, "I worked too much today." The patterns suggest it. And here's the point. Even if you delete the entire conversation, if the AI has access to your other conversations, or if it was trained on similar patterns, it will continue making those inferences. Because it isn't remembering the specific conversation, it is recognizing statistical patterns. Now the question you're probably asking, does this mean nothing is ever truly private? That everything you say to an AI is recorded forever somewhere inaccessible and impossible to delete? The answer is complicated. Technically, in a well-designed system, when you delete a conversation, those specific data points are removed from the servers. They are no longer accessible. They can no longer be read. But, and this is a massive but, if those data were already processed, already passed through the model, already contributed to updates or fine-tuning, then they left marks. Invisible, distributed, statistical marks. It's not that the AI can recover your exact words. It's not that there's a secret file with everything you said. But the patterns you contributed, the tendencies you reinforced, those persist, like ripples in a lake. You throw a stone, the stone sinks, but the ripples keep spreading, growing fainter, yet technically detectable if you have sensitive enough instruments. Let's think mathematically. Suppose a model has 1 billion parameters. Your conversation, when processed for fine-tuning, adjusts perhaps 1 million of those parameters by infinitesimal amounts, like 0.001 up or down. Now you want to erase your contribution. How? You would have to identify exactly which parameters were affected and reverse each adjustment. But there's a problem. Thousands of other conversations also affected those same parameters. You cannot undo your contribution without undoing everyone else's. It's like trying to remove a specific drop of water after you've already poured it into the ocean. And here's where Richard Feynman would slam the table and say, "This isn't a bug, it's a feature. It's exactly how learning works. Real learning, whether in biological brains or neural networks, is not about storing facts like files. It's about adjusting parameters, strengthening connections, creating patterns. And those patterns cannot be undone without undoing all related learning. Think about yourself. Do you remember the first day you learned to ride a bike? Probably not in detail. But you still know how to ride. The episodic memory of that specific day may have vanished, but the procedural memory, the skill, remains. It's distributed across millions of neurons in your brain, each contributing a little bit to balance, motor coordination, sense of direction. You cannot delete knowing how to ride a bike without damaging all those connections. And even if you don't ride for decades, the skill lies latent. AIs work in surprisingly similar ways. Not identical, of course. But the parallels are profound. When an AI learns something, it isn't an entry in a database. It's a distributed pattern throughout the entire network. And distributed patterns don't simply disappear. They can weaken over time if not reinforced. They can be overwritten by stronger patterns. But completely erased? Almost impossible. Now let's talk about something that will blow your mind. Recent research shows that even when you use sophisticated unlearning techniques to make a model completely forget a specific topic, there are always residues. Always. Because information in a neural network doesn't exist in isolation. Everything is connected to everything. Unlearning pizza potentially affects related concepts. Italian food, cheese, fast food, food preferences in general. And you don't want the AI to forget all of those just because you want it to forget pizza specifically. It's the granularity problem. Both biological and artificial information is holographic in nature. Every piece contains information about the whole, and the whole contains information about each piece. You cannot surgically remove one concept without leaving scars across the entire network. Let's consider the ethical implications. If AI memory never fully disappears, what does that mean for privacy? For the right to be forgotten? These are urgent questions, and the honest answer is that we don't yet have perfect solutions. We can delete training data. We can remove conversations from servers. We can implement strict privacy protocols. But if a model has already been trained on your data, already internalized patterns, already adjusted parameters, then part of you is literally encoded in that model. Impossible to retrieve as specific information, but present as statistical tendency. Think about the paradox. Companies promise you can delete your data. And technically, it's true. They remove your files, your conversations, your logs. But the model has already learned. It has already seen your writing patterns. It has already processed your preferences. And that knowledge is baked into the neural architecture. Not as recoverable facts, but as subtly shifted probabilities. And there's another layer. Let's talk about generative models that create new content. When you ask an AI to write a poem, it isn't copying poems it has seen before. It's synthesizing, taking patterns learned from millions of poems and recombining them in novel ways. But if one of the poems in the training data was yours, your style, your unique metaphors, your linguistic tics, all of that contributed to the possibility space. The generated poem isn't your poem, but it carries microscopic traces of your style. How do you quantify that? How do you measure the influence of a single work in an ocean of training data? The mathematics exists, of course, but in practice, with billions of parameters and trillions of training tokens, isolating the influence of one specific conversation is computationally infeasible. Theoretically possible, practically impossible. Like finding one specific water molecule in the Pacific Ocean. And here's something that will make you think. Every time you interact with an AI, you are training it. Not officially, perhaps, but through feedback mechanisms, you are shaping its future behavior. You deleted the conversation. But your preference for concise versus elaborate answers, your taste for scientific versus literary metaphors, all of that feeds the system. And training signals are permanent. Is this invasive? Depends on your perspective. On one hand, yes, marks remain in subtle ways. On the other hand, this is exactly how any learning system improves and evolves continuously over time. Without feedback, without real usage data, AIs don't evolve. The trade-off is inevitable. Perfect privacy versus optimal functionality. You cannot have both completely. But let's return to the physics of it, to the pure mathematics. When you understand that memory in neural networks is distributed, you realize something profound about computation in general. Traditional computers store information in specific locations. Address 0x7ff4, for example, contains the number 42. You can go there, change it to 43, delete it completely. Simple. Deterministic. Neural networks don't work that way. A piece of information isn't in one place. It's distributed across weights, activations, connections. Changing that information means backpropagating through the entire network, adjusting hundreds of thousands of parameters in cascade. And once you've done it once, you cannot perfectly undo it, because other information has already been overlaid. Other patterns have already been written on top. It's like recording on magnetic tape. You can record over it, but there's always residue, a ghost of the previous recording, detectable with sensitive enough equipment. Researchers call this catastrophic forgetting when talking about neural networks. If you train a network to recognize cats, and then train it to recognize dogs without showing cats again, it forgets cats. Catastrophically, loses the ability completely. But, and here's the crucial detail, it doesn't forget perfectly. There are always traces. There are always residues in the weights that, with the right technique, can be reactivated. Like repressed memories in the human brain, apparently gone, but recoverable under specific conditions. And there's more. Let's talk about adversarial attacks. Adversarial examples are specially crafted inputs that exploit the quirks of how neural networks process information. You can take a panda image, add imperceptible noise to the human eye, and make the AI classify it as a gibbon with 99% confidence. Why? Because the AI doesn't see images the way we do. It sees patterns in high-dimensional spaces where tiny changes can have massive effects. Now apply that to memory. Suppose you really want the AI to forget something. You use machine unlearning techniques, you retrain on filtered data, you manually adjust weights. But someone skilled enough, with access to the model, can craft adversarial inputs that reactivate those supposedly erased memories. Like exploiting security vulnerabilities, like finding backdoors. The information was never truly deleted, it was only buried. And what is buried can be unearthed. This sounds like science fiction, but it's current scientific reality. There are published papers demonstrating exactly this. Extraction of training data from supposedly private models, recovery of deliberately removed information. Not always, not perfectly, but often enough to be concerning. AI memory is resilient in ways creators don't always anticipate. Now let me tell you something really wild. Some researchers are exploring the concept of emergent memory. Not programmed memory, not intentional memory, but memory that emerges spontaneously from complex interactions within the network. Like when you connect enough neurons in sufficiently complex ways, self-organizing patterns begin to appear. Is this scary? Maybe. But it's also fascinating, because it reveals something profound about the nature of information and learning. Information isn't a thing, it's a pattern, and patterns are resilient. They persist, they propagate, they transform. You cannot kill a pattern by deleting a file. You can only dilute it, weaken it, overwrite it with stronger patterns. And here's the beautiful irony. Everything I'm telling you right now, this entire script, if used to train an AI in the future, will become part of its patterns. The specific words will disappear, transformed into vectors, embeddings, weight adjustments. But the essence, the argumentative structure, the logical progression, that will persist. Distributed, diluted, but present, like an echo through the multidimensional mathematical space where these machines live. So, returning to the original question, does AI memory never truly disappear? The answer is yes and no. Yes, because once learned patterns leave permanent traces, distributed, practically impossible to remove completely. No, Because the specific episodic memory, that particular conversation you had, that can indeed be deleted, removed, made inaccessible. But the learning, the adjustments to patterns, the statistical tendencies, those remain, weak perhaps, diluted among billions of other patterns, but present, always present. Because this isn't a bug. It's how learning works. It's how intelligence, artificial or biological, gets built. On patterns that persist, that accumulate, that transform, but never truly disappear. And perhaps, just perhaps, understanding this will make us think differently about our own memories, about how our brains work, about what it really means to remember and to forget. Because in the end, AIs are mirrors. Imperfect, distorted mirrors, but mirrors of our own cognition. And when we look at how they remember and forget, we are really looking at ourselves. Memory is not a file. It never was. It is a living, distributed pattern in constant transformation. And patterns don't disappear. They echo through time, through biological and artificial neural networks, through generations of models and brains. Faint, diluted, but eternally present. That is the surprising, strange, and wonderful truth about memory. And now you know.